Good afternoon. Thank you for attending this final session. My name is Dave Tepke with SKA Consulting Engineers, and I'll be presenting on the safety and sustainability for existing concrete structures, reflections and outlook. Before I get started, I would like to acknowledge that some of the information developed was in collaboration with Keith Kessner of SGH, Liang Jiang of Structural Technologies, and Steve Zoke of American Concrete Institute in conjunction with a building safety series that was developed and published in Concrete International last year. So some of the things that we're talking about here with respect to safety of existing structures was bred from that work. Before we get started, I would like to just comment briefly. The presentation today is going to be somewhat philosophical in nature. Maybe you'll come away with more questions than answers, and that's okay, because I think as a developing, certainly as a practice with developing information, we should all be thinking about how to make things better and how to progress the industry. Just by show of hands in the room, how many people in here work on existing structures to some degree? Okay. How many people have been doing it more than 20 years? How many people have been doing it less than 5? Okay, so we have people in here that have been doing it, that are relatively new to it, all the way up to people that have been doing it for quite some time. And so that's a testament to the buildings that we have and the need for it. And we'll talk a little bit as part of this presentation about how different people might view buildings because of their experiences. First, I want to start by saying that construction professionals in the Carolinas have very challenging yet interesting jobs. We have thriving cities, tourist attractions, historic structures, critical infrastructure, but we also have natural disasters on our coastlines and even inland. We have freezing and thawing conditions that span the state. Corrosive conditions on not only on our coastline, but also interior to into the Carolinas from de-icing salts that are used on our roads and in parking structures. And we also have material challenges. We have reactive aggregates that are used in making concrete right here in North Carolina, and there are certain things that need to be done to mitigate those certain types of distresses when those reactive aggregates are being used. So I guess as a person that looks at existing structures in the Carolinas, it's a very interesting job indeed. So why are we interested in safety and sustainability of existing structures? Why is this coming up more? It's seemingly more now than potentially ever. Well, when you look at the industry motivation for pretty much anything, usually change in the industry or need for new technologies is partially influenced by recent events, societal needs, and identified gaps. So while we can certainly ascribe the need to look into safety and sustainability of existing concrete structures because of these, this could pretty much be said for anything. Obviously, we have initiatives and societal needs for extending our resources. Certain events that have led to additional safety regulations and et cetera. And also in identified gaps in terms of the technologies we use. So if you actually look at this and, just kind of throwing some of the things together that are impacted by or impact those three primary drivers for change with respect to existing structures, certainly the environmental impact of the construction materials that we use to make structures and how long they last, and also paradigm shifts. We'll talk as part of this presentation about how paradigm shifts are healthy and useful for the industry, but also we have to watch out for them because they can lead to maybe deceiving our experience. And this leads into initiatives and regulations, and we'll talk a little bit about those with respect to safety and sustainability, new standards and resources, new trainings, and the impacts of economy and how new technologies can help us. So what does structural safety mean? Anybody in the audience want to just yell out when you hear structural safety? What do you think? If anybody wants to yell it out, what do you what is your impression when somebody says, "Is this building safe?" What are they asking? I heard, is it not going to fall down? Right. That's a very common definition, really. And we're going to talk here as we lead up how the code addresses safety, and also what an owner expects and maybe what an engineer thinks about when they're talking about safety. Well, that's a good definition. So what does the code say about safety and how does it qualify it? And the code, the International Building Code, and by extension, state codes that adopt it, use in section 101.3 of the 21 and 24 International Building Code, says the purpose of this code is to establish the minimum requirements to provide a reasonable level of safety through structural strength and protection from the hazards, et cetera, et cetera, et cetera, and dangerous conditions. So the code brings in this concept of reasonable safety, okay? And what is reasonable safety? Reasonable safety acknowledges the fact of the fact that absolute safety is something that is frankly we can't achieve, and we'll talk about why that is. So in section 202 definitions, dangerous conditions are those that are described as has collapsed, has partially collapsed, has moved off of its foundation, or lacks the necessary support of the ground. That's a pretty good definition in terms of dangerous, or significant risk of collapse, detachment, or dislodgement of any portion, member, appurtenance, or ornamentation under permanent, routine, or frequent loads for the actual loads in effect and environmental loads when imminent. And so this is the term significant risk of collapse. And how do we know what a significant risk is? And who determines what a significant risk is? And how do we quantify that? The International Existing Building Code goes on to indicate that unsafe is essentially buildings or structures that meet the definition of dangerous or that are otherwise dangerous to human life or to the public welfare, et cetera. And so dangerous conditions are those that are unsafe. The American Concrete Institute first published the what's termed the Concrete Repair Code. It has a longer title than that, but it's called the Concrete Repair Code. And it was first published in 2013. It's been updated several times since, and it's been adopted into the North Carolina Existing Building Code as a permissible approach, meaning that you're allowed to use ACI 562 in the assessment and repair, structural repair of existing concrete structures. But this document introduces a term called potentially dangerous, in which basically is another qualifier that allows us to further determine what is potentially dangerous or what does lead to a condition that is effectively reasonable, does not meet the, I guess, definition of reasonable safety. It has been determined to have a demand to capacity ratio exceeding the limit of 1.5. That means that the demand or the load compared to the capacity is 1.5. So what that effectively means is that the factors of safety, if you're looking at the typical factors of safety on loads, are being removed. And at this point, this code indicates that that is a potentially dangerous structural condition. There's some other definitions as well. So when we look at potentially dangerous structural conditions, and this is a condition where we had structural deficiencies from corrosion, which mandated or required shoring to support elements that do not have enough capacity on their own to resist the loads. Also, meeting the definition as written could be dangerous, potentially dangerous structural conditions from overhead spalling hazards. This is an example what we see. Does anybody do work on the coast or in parking structures? What do we, the more likely scenario when it comes to corrosive environments is that of corrosion creating spalling in overhead areas that could potentially detach and fall large distances and hit somebody. And when you actually look at the energy that can be generated by a 50-pound chunk of concrete falling 50 feet, or even a 10-pound chunk of concrete falling 50 feet, it's equivalent to, the energy the muzzle energy of some high-powered guns. So these falling hazards, these overhead spalling hazards, present a considerable condition of potentially dangerous. But the concept of reasonable safety, and the first answer that came out, and we're going to loop back around to this, but when an owner says, "Is my building safe?" What somebody who hasn't studied this or isn't sitting in rooms like this is really thinking they're asking is my building going to fall down, right? What an engineer hears and what an engineer is trying to communicate back in terms of what they know about the safety or what they can and can't know about the safety, and potentially what the likelihood or probability of a failure is something completely different. It's the term and the idea of this reasonable safety, meaning that there is no absolute safety in anything we're doing, in any building that we're in, and we'll talk about why that is here coming up. But certification of unqualified safety is impractical. And judgment and inherent uncertainties are nearly always characteristic in existing structures for a variety of reasons, because you can, and we'll talk about these in just a little bit. But if you're familiar at all with how new structures are designed, basically what we're doing is trying to create a situation where the capacity of a structure has a very low probability of being overcome or being less than the amount of load. Okay, and when you look at this in terms of design practice, what you're actually trying to do, and we have variability to all things, right? We have variability to the loads that we put on structures, and we have variability with respect to the resistance or the capacity of structures, because we don't know precisely what the strength is. We don't know precisely where everything exactly is in the concrete, and there's certain things in practice that we don't know. And so what you're trying to do is separate the load, separate the load from the resistance in a manner that the load is nearly always less than the resistance. And if where these curves do overlap is the probability of failure. So from a safety perspective, we design, people, say oftentimes, well, we design to make things stand up. And the way I look at it as an engineer is, we really design things to fail. And when I say that, I don't mean you design them to fall down, but you design them with the understanding and intention of what happens when there is a problem, right? You want to make sure or consider the redundancies or what we call ductile failures, et cetera. So if there is an overload, there are situations that can be dealt with and addressed before there is some sort of a catastrophic problem. And so more separation in these curves will occur if there are for more important structures, for more critical components, or ones with less ductile or less redundancy. You need to basically make sure or extend this separation such that the probability of failure or the probability of exceedance is very low. So how does this work in codes? Live load, for example, in a typical residential structure is 40 pounds per square foot. All right, if you're designing in many residential structures, you assume that there's 40 pounds on every square foot as the live load, or at least as loaded for maximum load effects. But we don't actually expect 40 pounds per square foot to be on there all the time, right? Actually, if you look at ASCE 7 in the appendix, you'll see that there's usually, 6 PSF, maybe 12 PSF expected. However, if you look at a building over 40 years, over a 50-year lifespan, at some point, somebody's going to, get a hot tub where they shouldn't. Or maybe somebody is going to move and drag all of the washing machine or the drying machine, the pool table, everything into the middle of the floor so that it's more convenient to get it out. Or maybe there's going to be a party or something that creates sort of a design event condition. Okay, so this idea that these loads are developed for the probability of them occurring long term. Similarly, for like wind loads, and we have Florida here as an example, but for different risk categories, you anticipate different wind loads. For risk category 2, which is a normal building, you're looking for a 1 in 700 annual probability of exceedance. And when you look at a risk category 4, such as a hospital or something that we need for critical operation, you're looking at a 1 in 3,000 annual probability of exceedance. So this is how the code handles the idea of probability of exceedance. So what is sustainability? We talked about safety. What does sustainability mean to you? Anybody want to yell out what they think of when what's the first thing that you think of when you think of or you hear sustainability? I couldn't hear. Yell. Pardon me? Lasting, right? Something lasts long. What else? That's a good one. Anything else come to mind? Environmental responsibility, that sort of thing, right? These are all things that impact the sustainability. So let's just take a brief look at what sustainability means. And I don't want to inundate us with definitions, so I don't think I need to read all these. But if you look at the Brundtland Commission definition of sustainability, for instance, humanity has the ability to make development sustainable to ensure that it meets the needs of the present without compromising the ability of future generations to meet their own needs, right? And the EPA report on environment glossary says the continued protection of human health and the environment while enhancing economic prosperity and social well-being. Sometimes these concepts are referred to as a triple bottom line, with economy, society, and environment being the 3 major players defining sustainability. For existing structures, for existing concrete structures, put together this additional, what I'm going to just for an existing structure, what I'll call a triple bottom line. When I'm thinking or looking at the sustainability for existing structures, you have structural performance and safety on one hand, you have environmental responsibility, and you have structural and repair durability, or making things last longer, right? These 3 things significantly impact the sustainability of existing concrete structures. Safety is part of sustainability for structures. Safety is the #1 critical societal need for the people today in leading to the future. So we got to be thinking about cost, function, environment, durability, and service life extension, but safety is a key component. So we might as well have just renamed this presentation to the sustainability of existing concrete structures because it's redundant to say safety and sustainability in that respect, in that it is included. So how is the safety being handled in different areas? And really all in terms of sustainability as well. Jurisdictional regulations and ordinances there are a number of them currently, and they're popping and they're continuing to be generated. Some examples are coastal condominium ordinances, such as the ones in Florida. There's parking garage ordinances, such as the ones in the Northeast. And there are facade ordinances in large cities where they require inspections on facades so that they can get a reasonable level of assurance that large chunks of facade aren't going to fall off and hurt passersby. So these ordinances are cropping up. The challenges with them are getting suitable language with respect to expectations and safety. I have read or seen a regulation that has required that a component or structure, et cetera, be required to be certified as safe, secure, and free of defects. I've never seen a building free of defects. I'm sure that one has not been built. And as we mentioned, SAFE has qualifiers with it, right? So we want to make sure that these regulations, as they're being developed, have meaningful words and they're able to be so that people understand what people are saying, and also to make sure that people I mean, as a design professional and an engineer, for me to tell somebody something is safe, secure, and free of defects is a really difficult thing to do. It's impossible, to be honest. And so making sure these regulations have meaningful words that are useful. There's also environmental regulations that are coming up. I think people have heard of EPDs with different construction materials that are being used, and how to minimize the carbon emissions with new construction materials, et cetera. ACI 562, as I mentioned, is the concrete repair code was adopted by the North Carolina existing building code as a permissible approach. So what's the impact on North Carolina? As I mentioned, North Carolina has a lot of the same challenges that other people have, right? We have the same challenges as what happens in northern parking garages. Maybe or maybe not as severe, right? We have the same challenges on our coastline as other states have. So, it's and I'm not aware of any, legislation on the table here in North Carolina. There was a potential House Joint Resolution on the table in South Carolina a couple of years ago to study this. I don't think it ever passed. I don't really know exactly what the legislation status is, but at any rate, these regulations will be continuing, I believe, to crop up. So making sure that they're flexible and have meaningful words is important. So what do often they start? These condition assessments of these existing structures start with a visual condition assessment, sometimes termed a phase one assessment. To look at the structure, look at the types of defects that are being that could present themselves, may be supplemented by some rudimentary non-destructive testing, but usually nothing major. And then if something is found that is concerning, then it could lead into a comprehensive condition assessment if required. So a variety of resources for this. American Concrete Institute, ASCE 11 was just updated for the first time in several years, quite some years, I think, which is a condition assessment guide. And then documents such as ASTM E2270 for facade inspection. So there are a lot of guides and resources that are being developed. And as I understand it, there is some push to codify condition assessments. Now, again, if you're going to codify condition assessments, you need to be very, very, you need to allow for the flexibility that existing structures with all their different types can come with it. So I understand that there may be initiatives in ICC and ASCE for codifying condition assessments. And so, again, these may become prevalent in the future. Other challenges with existing structures is variety of maintenance practices, which may or may not be apparent when you're looking at a structure. Previous repairs, and these repairs that I have shown are not good repairs. This is how you don't repair concrete. If anybody repairs concrete, if you look at the one on the left, the top left, it kind of looks like a skyline, maybe a New York City skyline in the repair geometry. That's creates reentrant corners and all kind of problems with cracking. The one good thing is you can tell where the stirrups are in that beam because I'm pretty sure that those repairs kind of mimic where the stirrups are. In the upper right-hand corner, similar thing. It looks like some stirrups were repaired, maybe by the Pi Iota fraternity that was doing some, I don't know, it's hard to tell. But so anyway, we have historical maintenance practices that may be suspect. There could be changes in use, such as on the lower right-hand corner. That was a textile facility with hydrochloric acid exposure that sort of decimated the bottom of that column. That facility was converted, that area was converted into my understanding was a parking structure after I looked at it. And so that certainly is a different exposure. And in concealment, when you're doing a condition assessment, there's often flooring, mechanical chases, all sorts of things that inhibit the ability to look at the structure. So these visual surveys may identify unsafe conditions, but they may not be viable for confirming quote unquote reasonable safety. There could be a lot of things that are unapparent. I have a mentor that would say that engineering is like an art and a science, right? And that's very true. You'd always say, you have to make it work and then you can do the numbers and stuff. If engineering is like an art and a science, structural evaluation and repair of existing structures is kind of like abstract art and that kind of science that makes me feel really, really stupid sometimes. Because, for as good as our equations are in new structures and identifying and understanding what we think we know with new structures, when you're looking at an existing structure, there's a lot of other things going on, right? Like look at this slab that's on the screen now, right? This is effectively a one-way slab that's going across the top of those beams. So what are we thinking about? We're thinking the bond capacity of that reinforcing steel, how it's compromised by the reduction in the composite nature of the concrete, the fire performance of it now, how much development length is being tied back into the bars, et cetera. Now this structure or these slabs were replaced, but thinking about it, it oftentimes is subjective in nature. Okay, and that makes it a very interesting part of the work, but also it makes it very focused on really trying to understand the principles. Sometimes it's pretty straightforward. This is a girder, transfer girder. And what you see is the blue marks that you see are just the locations of the stirrups, right? So if we make some assumptions about, what the strength of the concrete is, and we can pretty easily estimate the shear capacity here for identifying if these stirrups are or not where they should be, right? So sometimes things are objective. Sometimes we see cracks and, concrete cracks, in case we didn't know. It cracks quite often. Sometimes it depends on how the cracks are changing, where the cracks are. These are cracks in the middle of a beam. And, so does that mean necessarily that it's unsafe? No. I mean, sometimes it's designed to crack. But if it's getting worse, if it's changing, if it's in concerning parts, the types of cracks can certainly impact how we feel. This is, does anybody know where this is? Just taking a guess. Any NC State alums here? This is Mann Hall. This is one of the columns on the low roof with some significant cracking from corrosion. This structure was repaired, is in the final stages of closing out this repair. But these are cracks that are something that would need to be evaluated further and looked into. This is an example of some distress and deterioration around columns, which can be quite concerning on a flat plate slab system, as you can imagine. And so, sometimes things are quite, so the indication here, or what I'm trying to say is sometimes things are more apparent than others, but oftentimes there's a lot of subjectivity that comes into play and they're not straightforward. So when we do visual condition assessments on a building and you're walking out and looking at a building, and these red, yellow, green diagrams here are not meant as any sort of numerical or specific, specific measurement. This is sort of a big picture, how you kind of think about things or look at something. When you go out to a new structure and you're looking at something that was built with current codes, inspected by current code philosophies and special inspections, et cetera, you have a more comfort level, at least, that's something that it is likely to be more likely to be reasonably safe, right? There's always some possibility that the steel isn't where the reinforcing steel isn't where it should be, or the concrete wasn't strong enough in a critical location. But again, for a new structure, just conceptually, we think of it as being something that is likely has more certainty of reasonable safety, if that's the correct way to put it. When you look at a moderate age structure or a moderate age structure in an aggressive environment, maybe some distress, sometimes you're not really all that sure. And when you look at a building that's been there quite some time in an aggressive environment and there's a lot of damage, maybe you can be more sure, or I guess less certainty of reasonable safety, i.e. more certainty of potentially dangerous structural conditions. The interesting thing there is we put a tail onto the right side because sometimes there's things that just defy logic, that defy what we currently know in terms of our engineering practice, redundancies, secondary effects, things that you don't think about. So sometimes there's actually a level of safety there that you're not even able to take into account or think about from the code perspective, but it could potentially be there. This leads into the idea and what I was talking about before, and what an owner's asking and what you're able to communicate as a professional. And the difference in, I guess, the expectations and the words between saying something is safe and saying that I haven't seen anything that's unsafe. There's a whole different expectation of essentially of probability there. If you would go out and say something is definitively safe, or even reasonably safe, and you have a lot of things that are covering what you can see, that's different than not identifying anything that's unsafe in terms of the things that maybe you're not seeing that you can't know about, essentially. When you actually look at this structure, the way we use phase 2 condition assessments is that can help shift a curve one way or the other. And again, these are all conceptual, so I don't want to get hung up on the numbers, but if we go out and look at a structure that has some moderate distress, do some testing, look at the reinforcing steel, test the concrete strength, we can get to a point where we were looking at something that we now believe or really feel is potentially dangerous or has a safety consideration. There's also a possibility we can shift it the other way. You get good strength results. You test and the steel is where it should be. There's secondary effects that you're able to take advantage of. But again, even if you're shifting that thing to the right, conceptually, there's still things that you can't know no matter how much testing you do. So again, these are conceptual ideas just to help you understand sort of the philosophy that we, at least a philosophy, I guess, on how we can look at existing structures. I want to talk about how paradigm shifts impact our observations and what we think. Paradigm shifts are large changes in the industry, right? And these are very useful, very helpful things. They help us advance. They help us move from the way we were doing things in the 20s to the way that we were doing things in the 40s to the way that we're doing things today, right? And putting the puzzle together on historical aspects of what we know, how things were done in the past, can be very, very powerful. Understanding how an engineer in the 40s was designing something when you're looking at a building that was built in the 40s is very helpful. It's helpful to understand what the expectations were at the time in the code, but then also what we knew about different distress mechanisms, et cetera, in the industry. Further paradigm shifts help us really understand and really help us not deceive ourselves. We have to be cognizant of paradigm shifts. This is a fantastic figure out of from Well Yank's paper in 2018, showing in a country like the United States the construction boom. Right, the construction boom from the 1960s or so to the 80s to the 2000s, we were building a lot of buildings, right? So an engineer that was practicing or looking at buildings, say in the 1970s or 1980s, or even more contemporary than that, is looking at buildings that weren't all that old, okay? Looking compared to somebody today that's looking at a lot of our built infrastructure that's 60, 70 plus years old, okay? What does that mean? It means that just because you haven't seen something or experienced something in your long tenured career doesn't mean that it can't occur or it doesn't occur or there aren't additional issues. So we can't let our experience, I'll say, deceive us. We have to be cognizant of how paradigm shifts impact how we need to be looking at buildings, how we need to be looking at things. This is a picture on the left. This is a picture of Myrtle Beach area, coastal area that I took just a little bit ago. Or yeah, it might be the Florida. I can't remember exactly. It's either the South Carolina or Florida coast that we took. What do we see? We see a lot of tall buildings, right? A lot of our coastal areas were built, in the 70s, 80s, and 90s. When I look at existing drawings from the coastal areas, these structures are built in the 70s, 80s, and 90s a lot, making them, again, 30, 40, and 50 years old in aggressive environments, in which sometimes we're repairing buildings that are, we've done major repairs on coastal buildings before that are 25 years old, right? And when you do service life models on some of these buildings, whether or not the service life models are exactly right or not, it shows that corrosion in an unmaintained building can occur quite early in coastal structures. Okay, so this idea of we have now this aging coastal infrastructure as well, that we can't let our experiences deceive us, and because we've not seen certain things with regards to their deterioration. Other examples: special inspections introduced in the primarily in the 80s, but a little bit before as well. But think about today, we have special inspections. We have a lot of requirements for testing the concrete, testing the welds, making sure everything's where it should be, right? That wasn't the way when you're looking at buildings necessarily from a long time ago. And so when you're looking at a building, your assurance that something was done or your expectation should be different than potentially what it is today. Another example is structural integrity provisions in ACI 318 that started popping up in the late 80s. Everybody's probably heard of punching shear failure, or, it's not a good failure. It's a brittle failure, right? In the late 80s, the ACI 318 started requiring additional steel, bottom steel, going through the column area to create some post-punch collapse protection, right? Some structural integrity steel. So when you're looking at a structure maybe from the 60s or 70s, even though a designer that might have started in the 90s and been doing this for 30 years, understanding that it hasn't always been that way. I don't want to get too deep into durability discoveries, but my world is durability in a lot. For instance, freezing and thawing was first identified in the late 30s and reported on in the early 40s. It wasn't until the 60s and 70s until it really made its way into the code. And so structures that were built before the 1960s and 70s can have issues with lack of entrained air. Well, they can today as well, but but they became more integrated in the code towards the 60s and 70s. Corrosion, we've known about corrosion for a long time, started to be addressed more 50s through 80s. But really, we didn't start limiting the amount of chlorides with hard numbers in structures, basically cast-in salts from like accelerators until the ACI through 1883. So before 83, there were no specific limits on how much chloride you could put in concrete. Okay, so when you're looking at buildings, again, that predate that, these are important aspects. I can share with you afterwards, if you're interested, I can share with you a paper that has some information on this historical aspects. We also had we published something last year on the evolution of knowledge to codes. And this is kind of interesting, really. And there's a Concrete International article on this as well. It's kind of interesting how long it takes an idea to get into regulation. And it can be, in some cases where there's, let's just say it can be something as low as 15 years or 40 years or more, until that idea goes through consensus, consensus committees, and then it graduates into industry standard codes such as 318, and then a model code such as the International Building Code has to adopt it, and then a local jurisdiction or state jurisdiction like North Carolina has to adopt it, and it gets adopted locally. So again, this idea with even freezing and thawing damage, how long does it take? How long does it take for those provisions that were known in the late 30s and early 40s to get integrated into practice? It can take quite some time sometimes. I want to switch over in the last couple of minutes here and talk about repairs and what we in service life extension and how that, the last longer was the comment that came from the middle to the back of the room about part of sustainability. And that's dead on, and something I think that not a lot of people really take into consideration. I think sometimes when people hear and talk about sustainability, what they often are talking about or thinking is green, and they're talking about, they're talking about carbon demand. Very, very important things. But if you're not looking at the service life extension part of it, then it's not that you're not really taking into account. But billions of dollars a year are spent in the U.S. on corrosion control and concrete repair. Numbers float all over the place over the last 15, 20 years. What this is, it's probably on the order of $75 to $100 billion a year. I would say billions of dollars a day is a reasonable estimate for how much we're paying to repair concrete structures and to control corrosion. But the service life extension aspect that we're talking about, and this is just a really general service life extension curve. It takes a while, and this is for chloride-induced corrosion. Salts in our parking structures soaking into the concrete to get to the steel, or salts from the ocean soaking in to get to the steel. It takes a while for them to get there. Corrosion starts, it festers for just a little bit. And then once you start to get damage, you start to get a lot of damage, and it starts to become sometimes cost prohibitive to repair. But when you do repair it, the idea is you want to repair it and extend that service life out, or ideally extend the service life out before you basically help reduce the ingress of these things to extend it out as much as possible. So proactive service life extension, as was commented in the back, we could have ended 35 minutes ago after the comment came from the back about service life extension and sustainability. But anyway, we got another 15 minutes here. But proactive service life extension is inherently a sustainable act. ICRI, the International Concrete Repair Institute, came out in 2014 with a white paper. And one of the quotes that was interesting, and it's not surprising, really. The most sustainable management approach for buildings is to diligently perform preventative maintenance to avoid or at least minimize the need for repairs. That's pretty, that's pretty intuitive, but it's an important statement, and it's one that we should definitely be thinking about. Committee 160 is currently updating this document, so it should be published here quite soon. So how do we do it? We can use coatings to help keep the salts out. There's cathodic protection, thermal spray, The middle two pictures there are types of cathodic protection that can be used to arrest corrosion. And then sometimes sectional replacements. Maybe you don't have to get rid of a whole building, but maybe you can do sectional replacements with high performance concrete to extend the life of a structure. Repair versus replace comes up, right? When should we repair compared to replace? And we've already talked about deliberate service life extension being a sustainable act. There are potential situations where that's not true if things have gotten too far down the road from a deterioration mechanism, and conditions might be prohibitive even from an environmental and cost and service life extension approach if a building is in too bad a shape. But considerations, obviously function of the structure, making sure that it's functional to the owner. And what is the function of the owner? The service life expectation for what can be done to extend the service life, the amount of damage and the cost, and also the environmental implications. The quantification is a developing field. When we talk about EPDs and carbon emissions and carbon demand, et cetera, for new materials, personally, I think that there's certainly room to advance in becoming better at estimating those things and becoming, with some more precision. With respect to existing structures, I think there's even more opportunity for advancement and development and understanding how different service life extension methods can help from a service life and life cycle cost analysis perspective. These graphs that I've shown here, this is some research from Widdox 2022, where their research paper is very good research paper. They were showing how different approaches for repair, how much they cost, how much additional service life, and also the carbon demand. So this is the types of things that are going to be developing, I think, in the future. When we repair or, for new structures, even in coastal environments, looking at the durability of new construction, we know we have technologies in place now where if we think that, and don't worry about these specific numbers, this is from a service life model called Life 365. These things need to be looked at probabilistically. These individual numbers don't mean as much to me as the trends. For a code compliant concrete from today or from 20, 30 years ago, if you could expect X amount of time for until corrosion starts in the South Carolina coast, there are ways to 2X, 3X, 4X, even more that using stainless steel, other types of technologies, corrosion inhibitors, different types of cementitious materials and these things. This is what we should be thinking about when we're not only replacing components within a building for service life extension, but also in designing our new buildings. And again, just in the last couple minutes, I want to talk about how I think the industry is changing, and it always had and it always will, right? The way I look at this is that as the roots of knowledge grow deeper, our need to understand information spreads out, right? And when you look at, I always do the example, scientists in the 1600, we always go back to Newton. Look at Newton. He was doing experiments on optics. He went away into a barn house and developed calculus. He was doing all kind of different things, right? And he started developing these roots. And when you started to get to the 1700s, you started to see civil engineers, right? We get to the 1800s and late 1700s, 1800s, 1900s, we start to see mechanical and plumbing and structural engineers, right? And now we have codes. The concrete, the ACI 318 is about 700 pages long, right? And so at what point do those branches, because the roots of knowledge are getting so deep, at what point do those branches have to spread out? Is a structural engineer anymore enough to solve all the intricate problems. And I'm not just saying for a structural engineer, I'm saying everything. As these branches get larger, we start to think and talk about the additional need for information and the additional expertises that we need to facilitate that. This is just over the past 10 years, industry consensus documents. So ACI is the American Concrete Institute. ICRI is the International Concrete Repair Institute. And AMP is the Association for Materials Protection and Performance and Protection, or I can't remember which way. It's a newer, it's a new organization that was the combination of the old NACE, National Association of Corrosion Engineers, and SSPC, the Society for Protective Coatings, that merged into AMP. What I'm showing here is that over the past 10 years, I counted the documents that came out from those three. I would call these the big three organizations that are developing developing industry guidelines. There's been over 100, or there's been about 150 of these documents that have come out to help us be better at our job. That's fantastic, right? But it's also daunting. You're getting, on average, one new document per month that's coming out to help you do your job. You've got to be able to absorb all that and then apply all that, right? And that's exciting that we're getting this much information, but it also lends to the fact that we need to have avenues to have professionals that are specializing in doing these things. There's new and developing ACI standard codes. I talked about ACI 562, which was adopted in 2022 in the North Carolina existing building code as a permissible approach, meaning that it's okay to use it. You don't have to use it, but it allows you to use it. ACI 440.11, which is glass fiber reinforced polymer reinforcing bars. So a code to use those bars for concrete, and in certain conditions, in certain seismic conditions, you're allowed to use them. And that was adopted in the 2024 International Building Code. There's a new low carbon concrete code that was published late last year, and expected in 2027, there's a concrete durability code being developed. This concrete durability code is going to be meant to supplement ACI 318 when you want more durability or where you're in a particularly aggressive condition. Okay, so that's another code that's coming out to potentially help. There's a variety of environmental initiatives, ACI, ICRI, ISO standards, various life cycle analysis programs, and others. I'd like to briefly talk about, I sent a survey out to the American Concrete Institute Faculty Network last year, around this time or a little bit after, in which basically they have 1,488 educators in their network. And so this survey went out to everybody. It was basically asking them what kind of courses they have. And so an overwhelming majority of the respondents were from the United States. I don't want to get too deep into this, but the trend is, if you look the first, I know this might be a little bit hard to see, but it's not surprising that 80% of the respondents reported that their university that they're affiliated with has some sort of a structural engineering curriculum with 4 or more courses, right? But you look at how many have curriculum with assessment, or their self-reported assessment and repair, or sustainability, or durability, and these sorts of things, and it's much lower. That's not surprising, right? But it does highlight the fact that these are situations that we'll need to address as a society. And the next 2 slides, this is just a blow up. This is individual courses with 75% plus focus. Again, a lot teach ACI 318 structural design. Comparatively less teach repair, sustainability, and these sorts of things, which are very, very important for in our society moving forward. So do I think that there's some opportunity there, even in our educational systems, to help people basically soak up this knowledge base? We are in a career that demands experience. I mean, I think everybody out here that's looked at existing structures knows that you look at them a lot different now than the first one you looked at, right? I mean, and you probably design the repairs for them now a whole lot differently than you first did. So experience will never go away. It'll always be king, right? But there is opportunity for these fundamentals to be developed in university level. There's also initiatives to train the people that are actually doing the work. International Concrete Repair Institute has a concrete surface repair technician program, which helps inspectors and also even foremen, superintendents, these folks to know the important aspects of concrete repair and how to test for certain things. There's a developing program, the ICRI Repair Applicator Training Program, which is meant to train the actual applicators. The people that are actually installing the repairs or who this program focuses. And there were a couple of pilots that were done. One was done here in Raleigh last year, in which I can't remember exactly how many people went through, but there were a number of contractors that sent their applicators through. And this is now going live, in which it's an opportunity for contractors to have their people trained so the repairs that they install last longer, are more sustainable, to borrow the phrase that was offered before, to last longer. I want to end just on some recent and evolving technologies for building evaluation. There's a lot more tools coming out. There's a lot more toys today than when I started, and it's very interesting. And the interfaces with these toys are very helpful, right? The way we can use AI, these modules in some of this equipment to help interpret for us. LiDAR and photogrammetry is being used. Structural health monitoring, understanding strains and movements, as well as performance for materials related to stress. Drones, industrial rope access. These are all things that people are using, integrating into their structural evaluations. So looking to the future, again, we're going to continue to age, but the building, the infrastructure and our inventory is going to continue to age as well, and we need to be thinking about that. There's a ton of additional resources out there, and taking advantage of them is going to be very important. We need to emphasize, and I know we do, but we need to emphasize more durability. And there are things coming down the path with that that can be used for both service life extension of existing structures and of new structures. I think the advancement of environmental impact predictions is going to be necessary, so that we're actually getting truer ideas of what the carbon demand is on some of these materials, and also how is that integrated with service life. If you're using X% more carbon demand to build something or extend the life, how does that compare to how much longer the structure is going to last? And how can we balance that out to make it last longer? There likely will be more regulations and codes. There are a lot of codes being developed. Integration and also the need for education, I think, is very important. I think we're kind of up against time. I do want to mention that this was one of my first attempts at AI drawings. I asked for a strong, sustainable building, concrete building, and this is what it gave me back. And I think it's pretty good, right? I mean, it's a nice, strong green building. It looks pretty good. So, but I can't take credit for that, other than I typed it in and then typed some other things in to see what it could come back with. I'm happy to entertain questions. I know it's the end of the day, but if there's any questions, happy to stay around too, if you'd rather do it that way. Thank you very much. I appreciate your time.